Hi everyone, this is my lab 3 for Physics 2212. Let's first begin with the purpose. Using a small bar magnet, we will be exploring magnetic fields and the distance dependence of the magnetic fields, using both an experimental and computational model. The experimental model will measure the magnetic field using a magnetometer, and the computational model will compute magnetic field by applying the Biot-Savart law. At the bottom of the page, you can see a preview of some main results from this lab. Here are some fundamental principles used for this lab. The Biot-Savart law is an equation describing the magnetic field generated by a constant electric current. This equation can be manipulated to calculate the magnetic field caused by a magnet's magnetic dipole moment, as seen on the screen. There are also specific equations used to solve for the magnetic field at perpendicular and parallel observation locations, as listed on the screen. Lastly, for our on-axis experiment data, we will also utilize an equation that captures the distance dependence of a magnetic field. As for the assumptions for this lab, we must assume that the bar magnet acts as a magnetic dipole, so we can apply a manipulation of the Biot-Savart law. Let's review the experimental setup. For our system, we have the bar magnet, and the surroundings are everything else. For the initial conditions, we have that the bar magnet was producing a magnetic field that can be measured by the magnetometer. For finding the magnetometer chip in the phone, we slid our phone horizontally until the maximum X value was detected, and we placed a piece of tape as a placeholder. The phone was then slid vertically until the maximum Y value was reached, and again we used a piece of tape as a placeholder. The intersection of the pieces of tape was the location of the magnetometer sensor in the phone. For determining the magnetic field on axis, we first made sure the phone was aligned to the Earth's north-south axis. A meter stick was in place along the phone's edge, and the magnetic field was measured by the magnetometer at multiple different distances from the bar magnet. The data was then linearized using natural log and then graphed. Here's the data that we obtained from the experiment for the on-axis measurements, and here's the graph that was produced. We used the equations generated from the graph of the on-axis magnetic field measurements to compute the magnetic field of the bar magnet at a given observation location, and then we arranged the equation for the magnetic field at a parallel observation location to solve for the magnetic dipole moment of the bar magnet. This value came out to be 2.20. For the off-axis measurements, we moved the magnetometer along the meter stick to find a distance d perpendicular, for which the net magnetic field had a magnitude of 100 microteslas. We then added a meter stick perpendicular to the first one, and we moved our phone up along the second ruler so that the sensor was now a distance of d perpendicular from the horizontal ruler. We then used the magnetometer to determine the x, y, and z components of the net magnetic field at this location. We corrected the y component by subtracting the Earth's magnetic field from the total magnetic field measured for that y component. This is a computational model we generated for our data. Here we just have a constant that we'll use in our equation. Here's the magnetic dipole moment that we calculate using our on-axis data obtained during the experiment. And here we have a function to compute the magnetic field based off the defined magnetic dipole moment. And then here we just have a scale factor for our arrows we'll display in our output and a starting distance magnitude. This distance magnitude will then be observed at a positive x and negative x observation, a negative y and a positive y observation, and a positive z, negative z observation. And we'll calculate the magnetic field at each of these observation points. This next segment of code was used to calculate the magnetic field at a 45-degree off-axis observation location. First, we define this location, and then we use the dipole B function to compute the magnetic field at this point. The image below shows the vector magnetic fields at all the observation locations, including both parallel locations, all 4 perpendicular locations, and the off-axis location. These values are printed right here, and the magnitude of the magnetic field at the off-axis observation is also listed right here. The off-axis magnetic field measured in the experiment differs significantly from the off-axis magnetic field calculated using the computational model. The observed was actually over 4.5 times greater than the predicted. This is because the experiment is prone to more error and real-world effects, whereas the computational model is coded in perfect conditions. As for sources of error, we have that other electronic or magnetic objects could have skewed the magnetometer data. The location of the magnetometer chip in the phone may not have been found precisely, and handling of the phone could have interfered with magnetic field readings. Let's answer the first what-if question. If we hadn't compensated for magnetic north, this would have skewed our data, resulting in inaccuracy, since the Earth's magnetic field would have interfered with the bar magnet readings. As for the second what-if 2 identical magnets were stuck together, the magnetic field measurements should roughly double in magnitude, but still stay in the same direction. As for our conclusions, we have that distance is a very important factor in determining the magnitude of a magnetic field at different observation locations, and we also conclude that bar magnets can be used to accurately model magnetic dipoles, allowing for the application of Biot-Savart law. Thank you so much for watching.